beam analysis due to support settlement. This lecture is a continuation of our previous lectures on the slope deflection method. Here, we're going to see how this method can be used to calculate internal forces induced in an indeterminate beam when one or more of its supports settle. Suppose we have a continuous beam acting as a bridge structure. The beam has 3 supports, 2 rollers, and a pin. The left roller rests on solid rock, so does the right roller. The interior support, however, is a pin connected to a substructure that rests on soft soil. The beam is made of structural steel with a modulus of elasticity of 200 gigapascal. Assume a uniform cross-section for the entire beam having a moment of inertia of 56,000 quartic centimeters. After the bridge has been constructed and operational for some time, the soft soil under the structure settles, causing a downward displacement of the substructure by 50 millimeters. Consequently, point B displaces downward by the same amount. We wish to determine the effect of this displacement on the beam. More specifically, we want to compute member forces and support reactions caused by the support settlement. Once these forces are computed, we can then assess the impact of the settlement on the overall health of the bridge. To begin our analysis, let us observe the change in the bridge geometry caused by the settlement. Note that the downward shift at B forces segment AB to rotate clockwise and segment BC to rotate counterclockwise. According to our previous discussion on the slope deflection method, this means AB has a differential vertical displacement of negative 50 millimeters, and BC has a differential vertical displacement of positive 50 millimeters. To see how the slope deflection method deals with support settlement, let's write the slope deflection equations for each beam segment. For segment AB, we get what is delta here? It is the differential vertical displacement between the ends of the segment. In other words, it is our support settlement. So delta equals negative 50 millimeters. For the sake of consistency, I have converted the unit of displacement from millimeter to meter here. For member BC, we have here, delta is positive 50 millimeters. So when using the slope deflection method, dealing with support settlement is rather straightforward. Delta represents the differential settlement between the ends of the segment. So if one end of the segment settles by 50 millimeters relative to the other end, delta would be 50 millimeters. Here is a question for you. If the left end of the segment settles by 20 millimeters and the right end settles by 50 millimeters, what value should we use for delta? Since delta is differential vertical displacement, we should use 20 minus 50, or negative 30 for delta. Why the negative sign? Because these end settlements force a clockwise rotation of the segment. Back to our problem. Now we can write the joint equilibrium equations and solve them for the unknown rotations. The equations are when solved for theta A, theta B, and theta C, we get now, we substitute the rotation values in the slope deflection equations in order to determine member end moments. They are then, we can easily calculate member end shear forces for each segment. For segment AB, we have for BC, we have finally, we determine the reaction forces at A, B, and C due to the support settlement. Here is the summary of our analysis. These are the member forces and support reactions due to a support settlement of 50 millimeters at B. Let's examine another case. Here, we wish to analyze a continuous beam subjected to a uniformly distributed load. The structure has 4 supports, a pin support and 3 roller supports. Suppose the beam experiences support settlement at B, C, and D. B settles by 20 millimeters, C settles by 10 millimeters, and D settles by 40 millimeters. Similar to the previous problem, we start by determining differential vertical displacement for each segment. Segment AB rotates clockwise due to the settlement at B, so delta for the segment is negative 20 millimeters. Delta for segment BC is 20 minus 10, or positive 10 millimeters. And delta for segment CD is 10 minus 40, or negative 30 millimeters. Now, if we write the slope deflection equations for the 3 beam segments, we get Then, the joint equilibrium equations can be written as Solving these for the unknown joint rotations, we get When we substitute these values in the slope deflection equations, we get the following member end moments. Now, we can compute member end shear forces like this. And here are the support reactions. So the applied distributed load, coupled with the support settlements, result in these member forces and support reactions. See if you can solve the following problems.